Today, we will look at some problems about hydraulic jumps and gradually varied flow. The first problem, what is the difference between the alternate depths and the initial sequence depths? I have written the answer. The alternate depths have the same specific energy, one is subcritical and the other is supercritical. Initial sequence depths occur before and after hydraulic jump and do not have the same specific energy. So this is the difference between the alternate depths and initial sequence depths. For the second problem, a hydraulic jump occurs in a 5 feet wide rectangular channel, and the initial and sequence depths are 0.66 feet and 3 feet respectively. And we need to determine the energy loss and the flow number in the channel prior to the jump. So from equation 6.20 in the textbook, we know the energy head loss through the hydraulic jump, delta E, equals the difference y2 minus y1 to the power of 3 divided by the 4 times y1 times y2. And from the problem, we know the y2 equals the 3 feet and the y1 equals 0.66 feet. So we can get the energy loss delta E equals 1.62 feet. And from equation 6.17, we know the y2 over y1 equals 1 over 2 times the difference square root of 1 plus 8 times float number squared minus 1. The flow number is in the channel prior to the hydraulic jump. And from the problem, we know the y2 equals 3 feet and y1 equals 0.66 feet. So we can get that the flow number in the channel prior to the hydraulic jump equals 3.55 feet. And this is the supercritical flow. So we have done this problem. For the third problem, we need to construct the specific energy and the specific force curves for 5 feet wide rectangular concrete channel, and the Q, the flow rate equals the 40 cubic feet per second, and use 0.5 feet depth increments up to 3 feet. From the problem, we know the width of the channel B equals the 5 feet, and the Q equals 40 cubic feet per second. And we can create a table like this one. From the problem, we know the depths, the Y, is from 0.5 feet to the 3 feet, and we apply this equation. A equals B times Y, since we know the B equals 5 feet, so we can determine the values in the area column. And then we apply this equation. V equals Q over the A to determine the values in the velocity column. And then we apply E equals V squared over the 2G plus Y. We can apply this equation to determine the specific energy in this column. And for the last one, for the specific force column, since we know the Fs, specific force, equals the F plus rho times lowercase q times V, this equation also equals to the gamma over the 2, this is gamma, over the 2 times y squared plus the rho times the q flow rate over the B times V. So we can apply this equation to determine the values in the specific force coordinate. And then from this table, we can create two figures to show the specific energy curve and specific force curve. So this figure shows a specific energy curve, and this figure shows a specific force curve. Okay, so we have done this problem. From this slide, we will sketch water surface profiles, and I will follow all these 4 steps and draw everything on this single diagram. The first step, we need to draw the critical depths and the normal depths. So I use red dashed line to represent the critical depths. So this is YC, and I will use black dashed dot line to represent the normal depths. So this is normal depths. Since the slopes of these 2 channels are different, so the normal depths are different. And we know this is section 1, section 2, and section 3. So at the second step, we need to try the water depths is approximately equal to the normal depths at the far end. So we'll assume this point, at this point, and at this point, the water depth is a normal depth. Since we know the water depth at this point is less than the critical depth, so we will draw the water depth from the upstream to downstream, similar to this point. So at the third problem, we need to draw the water depth, and we start to draw the water depth from this point. Since nothing is changed in this channel, so the water depth just follow the normal depths to this point. At the fourth step, we need to complete the segment. Since we know for this point, the water depth is still less than the critical depth, so we will still walk downstream. And since we know this point is in the steep type 3 section, so the water curve should go up and approach the normal depth. So this is the curve S3. So now we have finished this problem. For this problem, at the first step, we still need to draw the critical depths and the normal depths. So I still use the red dashed line to represent the critical depths. So this is YC. And then I still use the black dashed dot line to represent the normal depths. So this this is Yn, and we know this section 1, section 2, and section 3. And the second step, we need to try the water depth is approximately equal to the normal depth at the far end. So we'll assume this point and this point, the water depth is the normal depth. And since we know the water depth is greater than the critical depth, so we will draw the water depth from the downstream to the upstream, similar to this point. And the third step, we need to draw the water depth. So we start from this point. Since nothing is changed in this channel, so the water depth just follow the normal depth from this point to this point. And the first step, we need to complete the segment. So for this point, we still know that the water depth is greater than the critical depth, so we still work upstream. And we also know this point is in the mild type 2 section, so the water curve should go up and approach the normal depth. So this is the curve M2. So now we have done this problem. For this problem, the first step, we still need to draw the critical depth and the normal depth. Sorry. So I still use red dashed line to represent critical depth, and I will draw the black dashed dot line to represent the normal depth. So this is Yn. We know this section 1, section 2, and section 3. So as a second step, we need to try what depth is approximately equal to the normal depth at the far end. So we assume at this point and this point, the water depth is the normal depth. And since we know the water depth at this point is less than the critical depth, so we will draw the water depth from the upstream to downstream, similar to this point. At the third step, we need to draw the water depth and start from this point. Since nothing is changed in this channel, so the water depth follows the normal depth to this point. And the first step, we need to complete the segment. Since for this point, we know the water depth still less than the critical depth, so we still work downstream. And we know this point is in the steep type 2 section, so the water curve should goes down and approach the normal depths. So this curve is the curve S2. Now we have done this problem. For this problem, we still need to draw the critical depths and normal depths. I still use the red dashed line to represent the critical depths. So this is critical depths, and I still use black dashed dot line to represent the normal depths. This is YM. Since this is steep channel, so the critical depth is greater than the normal depths. And we know this is section 1, section 2, and section 3. And at step 2, we need to try the water depth is approximately equal to the normal depth at the far end. However, it doesn't work out of this problem, so we need to choose the control point. A control point is a location where there is a known relationship between the water depth and discharge. And from the problem, we know or can compute the depth before the gate. So I choose this point at the first control point. And then we still know the water depth at the bottom of the gate. So this is the second control point. And the reservoir water surface will fall to the critical depths at the head of the steep channel. So this is our other control point. The reservoir water surface will fall to this critical point. And then we need to draw the water depths. So we will start the water depths from this point. And we know this point, the water depth at this point is greater than the critical depth. So we will draw the water depth from downstream to upstream. And we know this point is in the steep type 1 section. So the water surface should like this curve. So this curve is S1 curve. And for this point, this control point, we know the water surface will cross this point and fall into the steep type 2 section. And at this section, the water surface should go down and approach the normal depths. So this is the S2 curve. And then we need to complete a segment. So to link this water surface and this surface, there will be a hydraulic jump. And this hydraulic jump will cross the critical depths. So this is hydraulic jump. And for this control point, we know the water depth at this control point is lower than the critical depth, so we will draw the water surface from the upstream to downstream. And we also know this point is in the steep type 3 section, so the water surface should go up and approach the normal depths. Approach the normal depths. and then fall to the lake surface. So this curve is a 3 curve. So now we have done this problem.